In modern automotive systems, embedded security technology is important and paramount to ensure the safety and the integrity of the electronic control unit. Not only this, but many global level cybersecurity standards and even the government of India is mandating the cybersecurity standards to be implemented in our automotive electronic control unit. Some of these examples are IEC 21439, AES 189 by government of India. And for all these standards to be implemented in automotive electronic control units, there is need of embedded security technology. In the last video, we have got to know and explore number of articles, news, and the incidents in which our embedded systems are being hacked or being having a security design flaws in which makes the need of embedded security technology to be implemented. And in this video, we are going to explore different mechanisms on how this embedded security technology is implemented in our embedded systems of automotive vehicles so as to ensure the hack-proof and cyber-secure products. And for doing so, we are going to start by having a very crisp and a simple to understand analogy. By having an analogy of very two important electronic control units in an automotive vehicle, ADAS ECU and the Powertrain ECU. ADAS ECU is responsible for the driver assistance features like blind spot detection using time-of-flight sensors, forward or backward collision detection using the radar sensors for the fast-moving vehicles. And ADAS ECU take the input from different autonomous sensors like LiDAR, ultrasonic, time-of-flight in these sensors and analyze the environment around the vehicle and correspondingly send the commands to the powertrain of a vehicle which controls the vehicle's motion. On the other hand, we have a powertrain ECU which controls the engine, transmission and the torque delivery to the wheels based on the real-time data from the ADAS ECU. For example, in real time, the ADAS ECU detects some obstacle or some vehicle moving alongside with it, and correspondingly ADAS ECU will send the commands to the powertrain ECU to reduce the vehicle speed based on the surroundings environment. And this precise coordination between the powertrain and ADAS ECU is very much important for the smooth and the safe riding experience to the passengers. And now let's explore the different embedded security mechanisms by having these two ECUs, ADAS and powertrain ECUs, in a real-time vehicle. First scenario that we are gonna dwell into is the secure boot technology. First mechanism is a secure boot. When the car starts, both the ADAS ECU and the powertrain ECU boot from the firmware installed in them. What if someone attempts to change this firmware and both of these ECUs boot from the manipulated or the tampered firmware? Let's say someone has tampered the firmware of the radar sensor calculation of the engine control algorithm. It could lead to the catastrophic consequences and the damage to the vehicle and the passengers if coordination between powertrain and the ADAS ECU doesn't match very well. And technical aspect, secure boot is a cryptographic security feature that ensures that ECUs only run the authentic firmware which is installed in them by an OEM. And how does it achieve? It is achieved through cryptographic hashing. The ECU checks the cryptographic hash of the firmware during the boot. Digital signatures, the firmware which is running or which is first time booting in the ECU is signed by an OEM private key. And at the time of booting, the ECU checks the authenticity of those firmwares by the public key which is installed in them to check that whether the OEM authorized firmware is booting up or not. And now there is a part on the mismatch. If the firmware hash or the digital signature doesn't match, it will halt the ECU from running up and will show a message or a warning to the passengers or will send to the remote servers that there is certain tampering or hacking being done. And key thing in the secure boot is that it ensures that only trusted and authorized firmware is gonna be booted when the ECU or the microcontroller or the microprocessor which is there in the ECU powers up and starts. Next mechanism is the secure firmware update. OEMs very frequently update the firmwares or the softwares in the automotive ECUs. For example, for an ADAS ECU, an OEM might give an update for an radar sensor calibration or adding new autonomous features in a vehicle. And these OT updates are happened by the wireless communication protocols like Wi-Fi, GPS or the BLE. What if some hacker attacks these OT updates at these wireless communication protocols, and it can lead to the tampering of the firmware that is being updated via the OEM. And for this, so as to ensure the secure firmware update technology or the mechanism ensures that only legitimate and the verified updates by an OEM are installed and are being allowed in an ECU of Vanguard. And how this is done? Using an encryption. The firmware update is encrypted so that not any hacker or not any third-party person can understand what is the true firmware that is being updated by an OEM. Next is the digital signatures. Same way like the secure boot, in the secure firmware update also, the new features is signed are by an OEM private key, and ECU verifies the new firmware using the OEM public key installing them. Next one is the integrity checks, that during the transmission, the firmware is not tampered or is not being manipulated. So ECU we do the integrity cryptographic ciphers like hashing to ensure that the firmware being updated is not tampered with. Key concept over here is secure firmware update ensures that OT updates are being done without any tampering. Those are not being hacked and any wrong or the manipulated code is being updated into our ECUs. And this is one of the very two important mechanisms, secure firmware update and the secure boot, for booting up or for installing the new firmware updates in our ECUs in a secure and a safe protected environment. And the third mechanism comes is the device authentication. Imagine now that after the booting of our embedded nodes or the firmware in the microcontroller, the first thing that an embedded node or a ADAS ECU is gonna check is that whether it is communicating with an authorized and the genuine powertrain ECU. Consider that a hacker accesses a vehicle and he or she replaces the powertrain ECU with a fake and the manipulated ECU. So ADAS ECU might continue to communicate thinking that it is a genuine ECU, and this can lead to the catastrophic consequences and leaking of the sensitive data information. And here comes the device authentication mechanism. It ensures that only trusted ECUs after the booting or after the firmware update will be allowed to communicate within the vehicles for their networking. And this is implemented using the mutual authentication techniques, in which two embedded nodes like ADAS ECU and the powertrain ECU will be at first checked that they are the OEM authorized ECUs to communicate the real-time sensor data. And this is done via the use of cryptographic symmetric primitives like RSA or ECC ciphers, via the use of digital signatures, digital certificates, or the shared secret key techniques. And mutual authentication technique ensures that only authorized ECUs are allowed to communicate the actual real-time sensor or the information data between them. And followed by mutual authentication comes the access control, that if the powertrain ECU or the ADAS ECU don't authorize with each other and detects that it's a fake ECU it is being communicated with, it will cancel the access and it will block the further communication with the fake communicating ECU, which is pretending to be the original and the authentic ECU. The key concept of device authentication is that it ensures that only trusted ECUs or the drones or the embedded nodes are allowed to communicate the real information between them. And the third mechanism is the secure communication mechanism. Now, in a real time, in a vehicle, the ADAS ECU and the powertrain ECU exchanges lots of data. For example, radar, object detection, powertrain related ECU, engine related information, and all these information is being communicated between these two ECUs over wired protocols like CAN, LIN, Ethernet, or high-end automotive communication protocols. What if someone attacks at these communication channels at this physical layer and try to tamper or listen to the communication channels in the sensor data silently? It can lead to the catastrophic consequences and even the manipulation of the sensor data. And here comes the embedded secure communication mechanisms. Embedded secure communication protects the vehicle data exchange between two ECUs in a real time. And how does it achieve? Using the encryption techniques. Encryption is a way of making the original data into unreadable format so that any intruder or any attacker can't understand it. And that's where when two devices are communicating some real-time sensor data, encryption techniques are used so as to make the original data into unreadable format. For example, use of cryptographic primitives like symmetric algorithms of AES, Advanced Encryption Standard, is very commonly used cryptographic cipher for doing the secure communication between two embedded nodes. And there are different types of AES modes which can be used depending upon the data and the amount of data and type of data that is being transmitting or receiving between two embedded nodes. And another is the MAX, message authentication codes, which ensures that the data is coming from a trusted source using a commonly shared secret key. So will provide the confidentiality but also the integrity feature for doing the secure communication between two embedded nodes. So key concept of secure communication mechanism is to ensure that two embedded nodes, be it automotive ECUs, be it drones and the ground station, are communicating in a secure channel way, that is not any intruder can understand or detect what the original message is being delivered. And now, after the secure communication, secure firmware update, and the device authentication, if all these things are ensured correctly, a hacker might also try to attempt to physically tamper the ADAS ECU or the powertrain ECU or any of the embedded nodes to extract the sensitive data via the debug pins, which could expose the cryptographic keys or the firmware secrets of embedded nodes. Here comes the tamper detection, which monitors the physical security of the embedded nodes like of ADAS ECU, powertrain ECU, drones, smart meters, or any other, and react when an attack is detected. And this is accomplished through certain set of techniques. First is the physical intrusion detection, in which the sensors monitors the signs of opening the casing or certain changes in the temperature or voltage spikes indicating a tamper is detected. Second one is the self-protection, in which tampering is detected when ECU is triggered in a defensive actions like erasing the sensitive data of cryptographic keys or entering in a locked state or trying to access the unauthorized life cycles of an embedded device. Third one is also debug interface protection, in which if an unauthorized access to the debug port pins or the firmware extracting pins is being detected, then the ECU or the controller inside these embedded nodes, the microcontrollers or microprocessors, will disable the interface to further exploration or the exploitation. And the key concept of tamper detection is that it protects the embedded nodes like of ADAS ECU, your drones, and smart meters from physical attacks which can authorize trying to access the unauthorized way for checking the firmwares or the firmware secret keys and the other. These mechanisms work together to uphold the four pillars of embedded security in any of the embedded node, be it of automotive, be it of avionics, be it of healthcare, IoT, or anything. The first one is the confidentiality, which ensures your vehicle data is private and encrypted. Second is integrity, that commands and update the data are never altered or tampered while in transit of communication. And next one is the authenticity, in which the embedded nodes trust each other based on their identity and the authenticity. So last one is the non-repetition, in which actions, that is the data that is being transmitted or received, can be verified and trace back the original sources of the data. And now you all must be having a question that which all engineering aspects make all these embedded security mechanisms to implement. And one of the answer for that is the cryptography technology, which ensures that from secure boot to the encrypted and secure communication to device authentication can be performed using the cryptography technology. So in our next video, we are going to delve into the cryptography technology from the use case and application point of view. We will explore how the different cryptography algorithms of symmetric, asymmetric hashing algorithms are used for which particular real world use case and how they are used in our software implementations. Till then guys, subscribe to the channel to start your journey to be skilled engineer and not just graduated one. See you in the next video. Mention your views, share this video so as to make the knowledge accessible to all.